Welcome to Sustainable MEP Integration. I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. I will be guiding you through how sustainable mechanical, electrical, and plumbing MEP systems can be integrated into sustainable building design, an important step toward achieving a net zero energy building. We reference key texts, The Architect's Studio Companion by Joseph Viano and Edward Allen, and Net Zero Energy Design by Thomas Hootman. Please refer to these two books for additional details. We discussed the net zero design approach in the zero design videos. The net zero energy approach on the left consists of bioclimatic design, energy efficient systems, and renewable energy integration. The design goal is to reduce energy use through bioclimatic strategies from the outset. Energy-efficient HVAC systems are then incorporated to further reduce energy use, which is today's focus. Then, the on-site renewable energy system is integrated to support building operations. The net zero carbon approach on the right requires additional strategies beyond the net zero energy approach. Additional strategies include the use of renewable bio-based construction materials and the integration of vegetative systems, both of which offset carbon emissions from the building overall. The final performance goal is to design buildings that achieve both net zero energy and net zero carbon. For more information, refer to the additional videos indicated in the slide. We reviewed this pie graph in the bioclimatic design videos. The energy end user patterns emphasize HVAC as a key energy end user, followed by lighting, water heating, refrigeration, and others. Understanding the energy use profile for a building is important because different HVAC options are available depending on specific needs, which will be discussed on slide 6. The graph on the right shows an overview of HVAC system components consisting of primary equipment on the left and terminal units on the right, then connected with distribution systems. Typically, primary equipment such as boilers and chillers is housed in a designated mechanical room due to noise control and maintenance. Terminal units such as diffusers, fan coil units, etc. are located in occupied space. The distribution systems, such as water pipes and ducts, are hidden in ceiling, wall, or floor plenums. This slide deals with climate and human comfort in the context of HVAC system design. We discussed this topic in bioclimatic design videos. The human body reacts to environmental conditions, such as temperature, humidity, air movement, and radiant heat. Our bodies respond through mechanisms like evaporation, conduction, convection, and radiation. The indices of comfort reflect the interdisciplinary nature from medical science and biology to environmental technology and meteorology to understand comfort. In essence, designing comfortable indoor environments require careful consideration of different factors such as climate elements, human thermal response, space configurations, apertures, material use, and others. These factors guide the HVAC system design. This slide shows the psychrometric chart, an essential tool for analyzing air conditions and strategizing passive comfort solutions. The graph on the left is an earlier, simpler version, accounting for temperature on the vertical axis and percent relative humidity, %RH, on the horizontal axis. The graph on the right is an ASHRAE version, which on the other hand accounts for 4 environmental factors: operative temperature on the horizontal axis, dew point temperature and humidity ratio on the vertical axes, and %RH indicated by curved lines. The areas highlighted with hatched zones indicate acceptable ranges of operative temperature and %RH for people in summer and winter during primarily sedentary activity. For example, when the temperature is 26 degrees Celsius with 30% RH in summer, this will likely feel comfortable, even though the operative temperature is higher than the typical summer set point. This helps us select natural conditioning strategies during the bioclimatic design process before activating mechanical air conditioning. Now let's transition to HVAC system design goals and how to choose appropriate building systems. This slide highlights the common goals in HVAC design and links them to recommended system types. The vertical cells on the left explain the specific needs by the design team. The horizontal cells list out the different HVAC systems. The solid dot in the blank cells indicates recommended systems to meet the needs. The hollow circle is marked on the system that is less frequently used. For example, the VAV with reheat on the second column is recommended for these 5 considerations: minimize first costs, maintain comfort, minimize system noise, minimize visual obstructions, and maximize flexible space use. Active chilled beams are like the VAV with reheat, except one goal, which is minimize visual obstruction. This means that if you need HVAC systems with minimum visual disruptions, active chill beams may not be a good option. The table provides a quick decision-making tool, suggesting systems being frequently used while others being less common, which depends on design priorities. This slide introduces 4 prevalent HVAC system types and their architectural space implications: variable air volume, VAV, constant air volume, CAV, multi-zone systems, and active chilled beam systems. Typically, a large building incorporates the VAV with reheat as a default system according to ASHRAE requirements. Each of these is a distinct approach to distributing heating and cooling in a building. VAV systems modulate airflow to different zones, which can save energy but require ductwork that must be accommodated in ceiling spaces. CAV systems supply steady airflow and are simpler, though typically less efficient. They might be considered when uniform conditioning is acceptable, such as warehouse. A multi-zone system relies on one central HVAC system to serve different zones simultaneously, which becomes less efficient and takes up more space. Active chilled beams are a water-based system to condition the space coupled with air ventilation ductwork. It occupies less space than the previous air-based systems because water pipes are more energy-efficient distributors. Continuing with HVAC variations, this slide lists systems that often involve water-based heating and cooling and localized terminal units such as fan coil units, closed-loop heat pumps, radiant heating systems, and fan tube convectors. A fan coil terminal unit connects to hot and chilled water pipes, which provide better thermal comfort and space savings as a perimeter unit. The closed-loop heat pump incorporates a network of water source heat pumps and distributes energy from water pipes. This arrangement is flexible but needs mechanical space for heat rejection. The radiant heating system provides warmth through floor or ceiling panels by circulating hot water. It frees up space by reducing ductwork, though architects need to integrate tubing within slabs or panels and consider surface finishes for effective heat emission. The fan tube convector is a traditional perimeter unit often placed under windows that heats or sometimes cools air by passing it over a coil using natural convection by a small fan. These convectors take up wall space along the building perimeter. Overall, this slide conveys how each system operates and what architectural accommodations are needed, whether it's space for piping, dedicated mechanical rooms, or allocation of perimeter or ceiling zones for equipment. Here we focus on a hybrid approach combining variable refrigerant flow (VRF) technology with underfloor air distribution. The slide illustrates a system where a VRF and fan coil unit system provides heating and cooling, and conditioned air is delivered via an underfloor plenum. The combination indicates a highly integrated energy-saving strategy. VRF handles the thermal loads with compact refrigerant lines feeding fan coils, while an underfloor system ensures air ventilation is delivered low in the space for efficient stratified cooling, unlike traditional diffusers above the ceiling. This results in improved energy performance and comfort, but it requires careful coordination in design, allocating space for a raised floor, and planning the routing of refrigerant piping alongside the air distribution plenum. This slide illustrates the integration of VRF systems with a dedicated outdoor air system, DOAS, instead of the underfloor distribution system we discussed in the previous slide. In this configuration, the VRF system manages zone-level heating and cooling via refrigerant-fed indoor units, while the DOAS unit is solely responsible for providing fresh ventilation air. The DOAS is typically more energy efficient than a traditional air handling unit because it conditions 100% outdoor air and supplies it either directly to occupied spaces or into the return plenum, serving the VRF indoor units. By decoupling ventilation from the primary heating cooling, the VRF efficiently provides thermal loads, and the DOAS ensures ample fresh air with strict humidity and temperature control. Let's look at another system combination: displacement ventilation with perimeter heating. The slide presents a strategy in an auditorium cross-section where conditioned air is introduced at low level where users occupy and allowed to displace upwards as it warms. In a displacement ventilation system, large volumes of air at a slightly cool temperature flow in near the floor via diffusers located along the floor or low on walls. This cool air spreads across the floor, and as it picks up heat from occupants and equipment, it rises toward the ceiling, carrying heat and contaminants up and out. The result is a stratified environment. The lower zone remains comfortably cool and fresh, while warmer air accumulates above occupant level to be exhausted. The perimeter heating addresses the cold downdraft that can occur near exterior glass on cold days. This slide introduces a pre-cooling strategy for ventilation air using thermal mass. In this example, a remote thermal mass is utilized to precondition incoming air to reduce energy input to cool or heat incoming air. The diagram on the slide shows a concept in which cool night air is passed over or through a concrete slab, chilling that mass during off-peak hours. In this slide, we see a heat recovery concept. A way to harness waste energy from return air is to integrate an energy recovery wheel into an air handling unit. The principle shown is that before exhaust air is released from the building, its thermal energy is captured to preheat fresh air in winter and pre-cool in summer. The space in this slide uses a raised floor system highlighted in blue, which is another popular distribution system in office layouts. Primary equipment is located in mechanical rooms or on rooftops, while intake and exhaust ducts are routed through plenum spaces. The integration of mechanical systems also affects overall space planning. This slide provides an example of a net zero design approach by comparing energy performance scenarios for a real project. A bar chart is shown plotting EUI in kilo-BTU per square foot per year for 3 scenarios. The baseline scenario, labeled as a code minimum or standard practice case, might have an EUI around 80 kilo-BTU per square foot per year, achieving roughly LEED silver level. Then, a high-performance scenario implementing better insulation per ASHRAE 90 standard, improved glazing, and a more efficient active chilled beams with dual-wheel energy recovery and intelligent lighting, achieving roughly LEED gold level. This brings the EUI down by more than 30% to around 50 kilo-BTU per square foot per year. The most aggressive scenario moves toward net zero, approaching LEED platinum, adding measures such as using river water for cooling, solar chimney ventilation, displacement cooling, solar hot water generation, a large solar PV array, and advanced daylighting design with all LED lighting, which might reduce EUI further to approximately 40 kilo-BTU per square foot. This indicates a reduction of over 50% from baseline. The slide demonstrates the step-by-step pathway to drastically lower energy use. It vividly shows that through integrated design and multiple system enhancements, a building can approach net zero energy performance. Another aspect of systems integration is through the lens of a building management system, BMS. The slide lists several subsystems in a modern smart building that a BMS can monitor and control. They are security systems, access controls, fire detection and suppression systems, HVAC controls, power and lighting controls, and elevator control systems. A truly successful, sustainable design is that every component and system come together seamlessly to achieve an ideal outcome. We've just seen how various strategies contribute to near net zero performance. When everything is coordinated perfectly, the result is a cohesive, high-performance building. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We look forward to advancing sustainable architecture together.